Assalamu alaikum. This presentation is on the glottal area waveform, which registers changes in the glottal opening during phonation. This is reflected on changes on the glottal airflow and consequently the voice. We'll also go through what factors can modulate the glottal area waveform. The rapid changes in the glottal area, the glottal opening during phonation, can be detected and registered by the use usually of electrolaryngography, electroglottography, or sometimes by high-speed cameras for photoglottography. These changes, presented in the form of a waveform, can then be analyzed not only to measure the duration of the glottal opening and close phases, but also the speed with which such changes can occur. We'll also go through the effect of such changes on the voice source harmonic spectral slopes with examples of normal, breathy, or pressed voices, and we'll end up with the factors modulating the glottal area waveform. This upper trace shows a typical glottal area waveform during phonation as obtained from an electrolaryngogram. It shows the changes in the glottal area when the vocal folds are coming closer together to close up the glottis before they start to peel away from each other to open up the glottis in the later part of the vibratory cycle before the cycle repeats itself again. The speed of such movements of the vocal folds to close and to open the glottis is not uniform. They accelerate while closing and they decelerate while opening, and these changes can be seen from the lower trace here, which is a time derivative of the glottal area waveform. When there is acceleration in the movement of the vocal folds to close the glottis, it shows a high positive peak in here. This positive peak is used to mark the start of the closing phase. And when they slow down while getting apart to open up the glottis, there will be a small dip in here, much smaller than the positive peak, and this would mark the end of the closing phase and the start of the opening phase of the vibratory cycle. So here you could see that the glottal area waveform is divided into an open phase when the vocal folds are close together and an opening phase when they are apart. These two phases can be further subdivided into a closing phase when they are attempting to close before achieving maximum closure, and an opening phase when they are getting apart from each other before achieving opening of the glottis during phonation. We'll try to add some more details in here. This is again the typical glottal area waveform. This is the real signal of a glottal area waveform, and this is a schematic glottal area waveform. This is the time derivative, how the movements of the vocal folds can accelerate and decelerate. And this is a graph of the glottal airflow during the same vibratory cycle. To this we would add the changes in the configuration of the vocal folds during certain moments of the vibratory cycle. Starting with here in the closing phase of the vibratory cycle, it starts with the lower lips of the vocal fold medial ends moving medially to meet each other before the upper lips can follow later to close up the glottis completely. This is due to the phase difference between the lower lip and the upper lip. This would mark number 1. And we're still in the closing phase here. You would see this positive peak and the speed of the movements of the vocal folds during closure, giving the abrupt closure segment in here, this very rapid closure, and this would be marked as number 2. And then number 3 is achieved with maximum closure of the vocal folds together to close up the glottis. So this 1, 2, and 3 are the closing phase of the vocal folds. Between 3 and 4, the vocal folds would remain closed. So this is the closed phase. And then starting from 4, the vocal folds will start to peel away from each other, again with the lower ends of the vocal folds starting and the upper ends following a bit later. At one moment in here, there will be deceleration and the movements, the speed of the movements of the vocal fold. You would see how the opening up is much slower than the closing up, which is very abrupt. The opening up is very gradual and it decelerates at one point in here. This would mark number 5, and number 6 would mark the complete opening up of the vocal fold and the start of the passage of the air from the subglottis to the vocal tract. So this would mark from 4 to 6 the opening phase, and then from 6 till 1 there will be the open phase until it starts all together again. So these are a way of describing the vocal folds movement in closure and in opening up of the glottis during one vibratory cycle. Here we would see synchronized information obtained from photoglotograms showing the glottis from above, and glottal area waveform obtained from an electroglottogram, and the time derivative of the electroglottogram showing the acceleration or the deceleration of the speed of the movement of the vocal folds while closing and opening of the glottis. In the start of the closing phase, the glottis is still open. You can see some glottic area in there, but the vocal folds are starting to get closer together. And you can see from the traces here that the closing phase had not yet started, and the positive peak has not been reached yet. This positive peak would describe the abrupt closure of the vocal folds and the start of the closing phase. It would be reached in here, and this photographs there, the vocal folds have now closed the glottis. You could see this segment of rapid change in the glottal area waveform and the very high positive peak and the time derivative. And then the closed vocal folds would remain closed for some time before starting to open up again in here. This would mark probably the end of the closing phase, when there is deceleration and the movements of the vocal folds to peel apart, opening up the glottis in this frame in here. And then progressively the opening phase would continue, opening up the glottis further until the open phase is achieved here. You could see open glottis, and we are in this area of the glottal area waveform and its time derivative. Identifying the exact point of the start and the end of the closed phase and the start and the end of the open phase is important in measuring the open and the closed quotients of the vibratory cycle. This can be straightforward if you have a clear glottal area waveform trace like this, with its clear derivative, the time-related changes in the glottal area waveform, with a positive peak in here reflecting the rapid and the abrupt closure of the vocal folds, and the gradual opening up of the vocal folds with some deceleration here, giving this dip. If that's the case and you have the positive peak and the negative dip, then you could mark the start and the end of the closed phase and the start and the end of the open phase of the vibratory cycle. But that's not always the case, particularly in some cases of dysphonia, when it is difficult to identify this dip. In most cases, you can still identify the positive peak. There are three other ways of measuring the start and the end of the open and the closed phases. Two of them would depend on the threshold between the minimum and the maximum amount of the glottal area. If you go from the minimum to the maximum 35% up, then you would have a straight line here that marks the start and the end of the closed phase, and from here till the other cycle you can have the start and the end of the open phase. You can have this line at the 35% level from the bottom, or you can have it at 50%, this was proposed by other researchers to have either 35% or 50%. There is a fourth way of measuring the start and the end of the closed and the open cycles, and this is to use the positive peak here, which is commonly present in most traces, to mark the start of the closed phase. But to mark the end of the closed phase by measuring a 0.3/7 of the distance between the maximum and the minimum. This is about 42%. So a 0.42% would mark the end of the closed phase and the start of the open phase. So these are the four ways of measuring the moments for closing and opening of the closed phase and the opening and the closing of the open phase. The duration of the open phase in relation to the total duration of one vibratory cycle gives the glottal open quotient. This has its effect on the voice source spectral slope. If this ratio lies between 0.4 and 0.7, as in normal voices, if it is less than 0.4, it usually indicates a pressed voice, and if it is more than 0.7, it's associated with a breathy and weak voice. This voice source spectral slope graph comes from the fact that the harmonics produced by the voice source changes as the frequency increases. This rate of change of the harmonics when the frequency increases gives the spectral slope. The lower harmonics here, the lower frequencies, are affected by the increase in the glottal open quotient. If you have a high glottic open quotient, like more than 0.7, then you would get a higher dominant first harmonic and a breathy and weak voice. And conversely, when the open phase is short, this would cause most of the glottal flow changes to occur within a smaller duration. This leads to energy boosts in the low frequency portion of the source spectrum. The shortening of the open phase would, in contrast, makes the second harmonic or even the fourth harmonic more dominant, and this would give a pressed voice quality. Another useful index that can be extracted from the glottal area waveform is the contact quotient, which reflects the duration of the time the vocal folds are in good contact in relation to the time of the whole cycle. This can be measured by having a line at the 70% from the maximum closure or 30% from the minimum closure, and at this point in time you can drop a line here to measure the time. In here, this time in relation to the whole cycle will give the contact quotient. In normal males and females, it would be somewhere between 43.8 and 46.3%, and this would correlate well with the vocal intensity positively. So the higher this is, the higher the vocal intensity. In things like vocal cord palsy, this contact quotient would drop to 20 something rather than 43 or 46. Contact quotient can be increased by good level of vocal training. It can also increase in some pathologies affecting the vocal folds, like larynx edema, for example, and in some muscle tension dysphonias when the voice is pressed. On the other hand, the contact quotient would be reduced if there is reduced contact between the vocal folds, as in vocal fold palsy or in presbylaryngeus, or in some muscle tension dysphonias associated with weak and breathy voice. What is also of importance is the standard deviation of the contact quotient between different cycles, as this would generally reflect an increase in dysphonia due to the difficulty in controlling the degree of contact from one cycle to the other. This is an example of a typical glottal area waveform for modal voice in a normal person, which would show the rapid closure of the vocal folds compared with the slow opening up of the vocal folds. This rapid closure provides harmonically rich acoustic excitation of the vocal tract. On the other hand, if the glottis remains open during most of the vibratory cycle, or if the vocal folds don't meet well in the midline, there may be a non-zero level for the glottic area during the vibratory cycle. This would lead to a short closed phase, a short contact period, and a longer open phase. The air would be escaping more during the vibratory cycle, and the airflow can be rapid and cause turbulence. To illustrate this further, these are traces of glottal area waveforms from a patient with vocal fold palsy before and after medialization procedure. Before the medialization procedure, you could see the short closed phase and short contact quotient. The contact quotient for this patient was 28 point something compared to the usual 45 or 46% contact quotient. After the medialization procedure, things improved. The voice is now better and no longer breathy and weak. The contact quotient here has improved to 48%, and there is a longer contact period, longer closed phase, and a shorter open phase. So what are the factors that this vocal fold contact pattern depends on? Primarily the degree of the vocal fold approximation by the adductors, the glottal channel geometry, its extent, its depth, and the duration of the contact, the subglottic pressure, and the vocal folds' intrinsic stiffness during adduction. Changes in any of these parameters can influence the fundamental frequency by affecting the vocal fold contact mode. The extent and the duration of the glottis closure and vocal fold adduction during phonation can be improved by the lateral cricoarytenoides and to a lesser extent by the interarytenoides muscle. These muscles improve the vocal folds contact, particularly with increasing subglottic pressure. The configuration of the glottic canal during vibration, during phonation, the depth of the glottic canal, and the pattern of contact between the medial ends of the two vocal folds are both affected by the cricothyroides muscle and the thyroarytenoides muscle that can change the glottal canal geometry. The cricothyroid muscle would tend to stretch the edges of the vocal fold and reduce the vertical thickness of the glottal canal. On the other hand, the thyroarytenoides muscle would increase the vertical depth of the medial ends of the vocal folds and also increase the medial bulge of the inferior part of the medial ends of the vocal folds during phonation. This increase in the depth of the vocal folds and the medial bulge would both increase the duration of the closed phase and the contact phase during phonation. And finally, the other way the vocal fold stiffness can modulate and adjust the voice produced by the vocal fold is through the effect of the anisotropic stiffness on the glottal closure. The anisotropic stiffness of the vocal fold optimizes the way the vocal folds closes during phonation. The way the fibers are aligned in the anteroposterior direction improves the glottal closure, and also the way the lamina propria has these fibers is between the core of the vocal fold, the muscular part, and the surface. The superficial position of the aligned fibers also improves the vocal fold glottal closure. Even the epithelial layer, the envelope of the vocal fold, the stiffness of this epithelial envelope also improves the glottal closure and improves the duration of the glottic closure and allows vibration for a considerably longer closed period. By this, we come to the end of this presentation of the glottal area waveform. Assalamu alaikum.